Okay, is my screen visible?
Yes, sir.
Okay, good. Okay, let us start. Uh, I would like to say this is possibly the last equivalent model that we are going to discuss. Now we are trying to uh, write some kind of grammars for recursively enumerable languages. Okay. So far we have seen that the regular languages are um, in a sense equivalent to linear grammars. Context-free languages are equivalent to context-free grammars. Okay. Now we will see that the so-called RE languages, recursively enumerable languages, are also equivalent to some kind of grammar. And these grammars are called unrestricted grammars. Okay. So I will start with how we can design unrestricted grammars. And I will give you an idea how to prove the equivalence between Turing machines and unrestricted grammars. Okay. Okay, so let us start. Okay, so as I mentioned, so you have grammars, languages, automata, and productions or rules of that grammar. So we have the so-called right linear grammar. So these are also called type 3 grammars in the so-called Chomsky hierarchy. These are equivalent to regular languages. And in terms of automata, these are equivalent to deterministic or non-deterministic finite automata, and you may add epsilon transitions. And you have seen that these rules are, have you seen it? Possibly no. Anyway, rules are of this form. A can be AB or A can be epsilon. Okay. So this first kind of rule is something like move from state A to state B after consuming A. Okay. And if you are in a final state, that state may become epsilon. So whatever string is consumed so far, that is the uh, I would say accepted if you end up in a final state, if capital A is a final state, or rejected if capital is not a final state. Anyway, and then you had context-free grammars, which are also called type 2 grammars. They are accepted precisely instead of, I mean, the push-down automata. And here the rules are of the form A can be an arbitrary string of terminal and non-terminal symbols. Okay. Now there should be some type 1 and type 0. So the type 0 thing we will actually study. So in between Turing machines and push-down automata, there is actually a class of machines. These are Turing machine-like, but they have certain restrictions. So these machines are called linear bounded automata or LBA. Okay. These machines are essentially equivalent to so-called context sensitive or type 1 grammars. Okay. So here the productions are of the form. I can have some alpha and gamma surrounding uh, the non-terminal symbol that I want to replace. Okay. And in the context of this alpha and gamma, this capital A changes to beta. And context sensitivity for a reason requires this beta to be a non-empty string. Okay. And so this is called context sensitive grammar, because A can be expanded to beta only in the context of alpha and gamma. That is the reason it's called context sensitive. Okay. Finally, we have so-called Turing machines, not necessarily total, and these are equivalent to unrestricted grammars. So these are of the form alpha, A, gamma can be beta. So once again, I can append or prepend anything to a non-terminal symbol, which may again be, which may again contain non-terminal symbols. But this is unrestricted because, of course, it is alpha and gamma. This context it is changing, but the context also changes. The entire thing goes to beta. Okay, so this is unrestricted. Okay. And these are equivalent to Turing machines, as we will see shortly. So let us talk about unrestricted grammars. So again, it's similar to this fourth tuple, sigma, set of terminal symbols. N is the set of non-terminal symbols. And of course, we will assume that N is disjoint from the terminal symbols, the set of terminal symbols. Like context-free grammars or any other grammar, there is a start symbol, a distinguished member of N non-terminal symbols. It is called the start symbol. So every derivation starts from this S. Okay. Finally, P is a finite set of productions or rules of the form. Anything can be anything, provided only that the left side of a rule must contain at least one non-terminal symbol. Okay. You cannot simply, once some terminal symbols are generated, you cannot simply change them. Okay. But if those terminal symbols are accompanied by some non-terminal symbol, then that string can be anything. Okay. So that is why it is called unrestricted. Anything can be anything. Okay. Only thing that left anything should have at least one non-terminal symbol. Okay. And also you can write it this way in order to highlight that some non-terminal symbol must be there on the left side. It's the same way of saying the previous thing. Okay. And like context-free grammars, we can define the language generated by this grammar to be the set of all terminal symbol strings, that is all strings over sigma, that can be derived from the start symbol. So note that, like context-free grammars, starting from S, you will often have many non-terminal symbols. But in order to derive a string in the language, you must eventually get rid of all the non-terminal symbols. What you should be left with is only a string with terminal symbols. Okay. And you can apply these productions in any manner you like. Okay. So let us see certain examples to clarify why it is much more powerful than context-free grammars that you are already familiar with. Okay. So let us start with our first example. I will generate all strings of the form a power 2 power n for all n greater than equal to 0, and we have seen that this language is not context-free. Right? Okay. Whether or not this language is context sensitive, that is a different issue. But possibly we will do one or more, maybe one exercise on context sensitive grammars. Okay. Let us see. If time permits, we will do it. Otherwise, don't do it. Okay. So what is the idea? The idea is that this grammar will first generate something like a power n, capital A power n. I don't know what symbol I have used. Okay. Also, it will generate a single a, small a. Okay. It will also keep one non-terminal symbol at some. Now, in order that this capital S must not be there in the final sentence over W, what I will ensure that this capital A, maybe let's see whether I have used capital A, otherwise it will be confusing. Ah, yes, capital A. Okay. So this capital A will have to cross the small a's. Okay. So every time it crosses a small a, it will generate two a's, two small a's. Eventually, it will come with the other end where another non-terminal is sitting. Okay. And I believe it is capital T here, which is a kind of terminator. So only when this capital A comes in contact with this capital T, it vanishes. Okay, so you have to get rid of this capital A's, right? So all this capital A will have to come in contact with capital T. And in the process, what it will do, it will go through this so-called small a's generated so far. Every time it does so, it doubles their number. Okay? So starting from a single A, only one A, n capital A's are generated. So the first one will double the number, so it will be two small a's. Second one will again double the number of the small a's, so it will be 2 square, 4. Third one, in its process to terminate, will generate again a double number of a's. Okay. So it will be 2 power 3 and so on. So let us see how it is done. So the small a is generated here, and this is the so-called terminator. And for the moment, the task of U is to generate in a context free manner some number of capital A's. Okay. So it can be epsilon or capital A U. A generated some n number of times, and then this U vanishes by using the production. U can be epsilon. Okay. Then this is the production of how A can go from, capital A can go from right to left in order to meet capital T. Okay? So you see that A has crossed one small a, capital A has crossed one small a, and in the process it has generated an extra A. Okay? Okay, so eventually A will come in contact with T, it will vanish. There is no other way in which capital A can go and eventually get you a sentence. Eventually give you a sentence. Okay. And when this all Okay. Yeah. Yeah. So this is not a good design. Anyway, I will. Okay. So as for the team members, we just have this power. I mean this internet cable cut. Anyway, I hope you can once again hear me. Okay, there should not be any problem. Anyway, let's switch to this. Okay, so these are my set of rules for the context-free. Yes, yes. Hmm? Oh, once again, I have to share the screen, right? Oh, oops. Okay. 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 So let us see a generation of something like a power 2 power 3, let's say, a power 8 derivation. So you start with S, replace it by TAU. This is the only production possible. So this terminator T is generated, a single A is generated, and one U is generated. Now it will generate the requisite number of capital A's. Yeah. What if capital T goes consuming all the A's? Then there is no way a capital A can vanish. You can generate some sentential forms, but neither of these will be a sentence, right? Okay. Yeah, yeah. That's an interesting idea. Okay. So only the things that can be generated and are over. You may do a lot of bad things, so that further you'd say uh, progress is impossible. But then these things are not part of the language. Okay. Okay. So it will generate 3 capital A's, and then it will vanish. Okay. Now these capital A's will one by one move from right to left in order to get contact with capital T, and it will vanish. Okay. So let's see. So this AA, when it comes, it generates two A's, doubles the number of A's. Then I apply this production, TA can be T. Okay. Now it is the turn of the second A to go through the sequence of small a's. Okay. So it does. Eventually it gets in touch with this capital T, vanishes. Finally, the third one becomes this. And at this point, it is safe for T to vanish because it has consumed all the capital A's. Okay. That's what it does. Okay. Okay, so let us look at a second example. This A power n, B power n, C power n, which is once again not context free. You cannot generate this language in a context free manner. Okay. But given an unrestricted grammar, we can, given the option of using an unrestricted grammar, we can do it. Okay. So the idea is, once again, we'll have a terminator T, and initially I will have some U. Okay. So instead of generating A power n, B power n, C power n, this will generate A power n, BC whole power n. Okay. But this BC, if they are lowercase bc, okay, this lowercase bc are part of the input alphabet sigma. I cannot rearrange them, right? So at least the small b or small c should be generated as capital B or capital C, so that there is an option of rearranging them. Okay. This is what this U does. In a context-sensitive manner, it generates a power n, b capital C whole power n. Okay. And eventually it vanishes when some n number of A's and BC's are generated. Okay. Now this is simple. You can swap this capital C with capital B. That if you generated only small c, then you cannot have this rule. Small bc cannot be equal to small cb or whatever, other way around. Okay. But then, so this is allowing the c's to go through the b's and eventually this to move from left to right. Eventually it will come with this t and it will vanish. Ct can be t. Should not vanish. Okay, it should produce a c, small c. Okay. Yeah, Ct can be t, small c. Okay. C should not vanish actually. Eventually t can be epsilon when it is done with converting all the capital C's to small c's, only when these small c's are in proper position. Okay. So this is the second example, and let us look at a derivation, a cube, b cube, c cube maybe. Okay. Start from ut, t is the terminator. Will always sit near the end. A, U, B, A, U, B, 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 C, B, okay, B, C. And then eventually U vanishes. So at this point, what happened? A's are generated, they are in order, but this B and C's are not in correct order. So I have to move the capital C's towards right. Okay. CB. Okay. Eventually it becomes BC. Fine. Okay. So one by one, all the capital C's goes to T. Okay. Of course, you can actually change the orders. Okay. I mean, okay, let's see. So this T converts on capital T to small c, capital C to small c. Next one again, next one again. Now it is time for capital T to vanish. Let it do so. Okay. Okay. Maybe we will solve one exercise on generating some context-free, non-context-free language using this kind of grammars on Thursday. Okay, so now I will give you a brief idea why or how these unrestricted grammars are equivalent to Turing machines. Okay. So there are again two directions of the proof. Given an unrestricted grammar, I have to show that a Turing machine can derive the sentences, okay, following those productions. Okay. And the second direction is, given an given a Turing machine, I can design an unrestricted grammar which essentially simulates the working of the Turing machine. Okay, so that's a more difficult part. Okay, so these are the two things. Given an unrestricted grammar, there exists a Turing machine M having the same language and vice versa, conversely. Okay. So unrestricted grammar to Turing machines. This is not a difficult part actually, because a Turing machine can do many things. So it can actually follow this derivation process that you have seen in the pictures. Okay. Only thing I would say, make it a little bit more formal and detailed. Okay. So maybe I can design this Turing machine M as a non-deterministic machine, because we know that non-deterministic machines are as powerful as deterministic Turing machines. Okay. So I can design it as a non-deterministic Turing machine, and then we can do actually that computation tree kind of stuff to convert it to a deterministic machine. Anyway, and the input is provided to the first step. So these are some details. Just go through this. And the second step will consist of those strings that are generated in the intermediate stage of the derivation process. Okay. And of course, the derivation starts with the start symbol capital S. So the second step is initialized to S, capital S. Okay. And the third and fourth steps are used in order to do this substitution of the left side by the right side of a rule. Okay. So how do I use it? So non-deterministically choose a position on the second step. So the substitution will start from there. Okay. If it is not possible, definitely the machine will get stuck. But if it is possible, it will make a substitution from that point onward. And non-deterministically choose the production. Alpha can be beta. Okay. So the idea is you choose these two positions, or the rule alpha can be beta, and the position where you want to substitute alpha by beta. Okay. These things may be non-deterministically chosen. Okay. So if some sequence of guesses works, this will work. Right? And do this substitution, copy alpha to tape 3, beta to tape 4 maybe. Okay. Compare tape 2 and tape 3 starting from that non-deterministically chosen position. If they do not match, then of course the substitution is not possible. Okay. Otherwise, if the comparison succeeds, replace alpha by beta on tape 2. And if the length of alpha and length of beta are different, then you have to shift whatever follows on tape 2. Shift left or right, depending upon the lengths of alpha or beta, alpha and beta, comparative lengths. Okay. After that point, this machine has applied one rule. Then it will just compare whatever sentential form it has with the input. Okay, if at that point of time it is the sentence just to the rules, then it will accept. Okay. If they have identical contents, accept. Okay. So that's the simulation. Fairly straightforward. Turing machine can do a lot of things. So in particular, just carrying out this derivation process is not so difficult for a Turing machine. It's a powerful machine after all. Okay. But you note that this M is not necessarily a Turing machine. It can keep on making substitution after substitution forever without ever reaching the equality in tape 1 and tape 2. Of course, if the string in tape 1 or on tape 1 can be derived using the grammar, then some non-deterministic choices will allow this machine, non-deterministic NTM, to derive that. But if that input is not in the language of the grammar, then there is a possibility of loops. It keeps on substituting without ever generating the string given on the first step. So this is not necessarily a total Turing machine. Okay. So I do not say that recursive languages are equivalent to unrestricted grammars. Okay. So I say that recursively enumerable languages are equivalent to unrestricted grammars. Okay, but this is one direction of the proof. The second direction is a little bit more, I would say, technical. The most difficult thing about this part of the proof is that a grammar starts with a start symbol. It will eventually end up with a string over sigma. On the other hand, a Turing machine starts with that thing, an input string. Okay, and it does something on the I would say input string in order to eventually arrive at an accept or reject decision or looping. Okay, so for the grammar, the string of concern over sigma, that is the last thing. That is the last thing of the derivation process. For this machine, this is the first thing. Agree? Okay. So, in order to cope with that, what the simulating grammar will do, okay, it will actually start from the final accept configuration of the machine and reverse the working of it, and it will eventually see whether it can generate the initial configuration. Okay, so that's the only technical difficulty here in this proof. Okay, the machine will move forward in this direction, but the grammar will start from the end and it will rewind the steps of the machine, come to the initial position. Okay, so here are certain details. Again, now I can assume M is as simple as possible. A one-step non-deterministic deterministic Turing machine, and because this grammar makes sense out of this, what I do, I make some small changes to M. Okay. For example, when it accepts, it completely erases the tape. Okay. This it can do, right? So I will call that old accept state something like T prime. And after that, I will keep on erase until I reach the left end marker. And then I will switch to that accept state, a new accept state. This I can always do by slightly changing so this is what I mean at a new accept state. Whenever M reaches the old accept state T, erases the entire tape, and after seeing the left end marker, jumps to T prime. This much change I can do. Okay. And also there should be a way that the grammar knows that this is the end of the visited part of the string, of the tape. Okay. So as we have seen earlier, so I will also always maintain a right end marker to indicate the end of the visited part on the tape. Okay. Whenever the visited part grows, that right end marker will be shifted one step to the right. Whatever you want to write there, you write. Okay. So, yeah, so this marker is shifted right if you want to extend the used portion of the tape. And during erasing at this step T, this marker is moved left until it touches the left end marker. Okay. So, as I mentioned, G simulates the working of n, not from n to beginning, not from beginning to n, but from end to beginning. Okay. And the configurations of M are the sentential forms. Okay, and the configuration will be maintained like that. A string starting with the left end marker, followed by a state, followed by the symbol currently being scanned, followed by whatever is remaining on the tape, visited part of the tape, followed by that right end marker. Okay. In that is the thing. This is the accept configuration because it has erased everything on the tape and eventually switched to the STIP prime. Agree or not? This is the only way it can accept. Okay. Left end marker, right end marker. That is the only thing on the tape. And the tape position is just before the right end marker, or on the right end marker. Okay. So this is the accepting configuration. So what the grammar will do, it has a start symbol S that will go to this. And then it will simulate the machine backward. What is the initial configuration? Okay, so you see, these are just details. Just add this rule, S can be this. Happy? You can do that, but the idea is that you keep on erasing and moving that thing, and whenever you see that left end marker, you stop that loop. Okay. And of course, let's say it does not stay stationary. So whenever you are on the left end marker, you move right. Right? So no, it can be. But the idea is that instead of stopping at the left end marker, it goes to the right end marker and it stops. Okay. Okay. How to? These are all symbols. Left hand marker, right hand marker. Oh, these are symbols. These are non-terminal symbols in the grammar. You see, what is the non-terminal symbol? The non-terminal symbol consists of all the tape alphabet symbols except the input, because configurations also contain a unique state. So the states P, Q, U, V, T, T prime, R. Okay, these are also called non-terminal symbols. Okay. And a new start symbol S that is not covered by the above two. Okay. Okay. Now, if now this grammar will made by the Turing machine. So if it ever accepts, what will be it will eventually end up in the initial configuration, and that is what S followed by the left end marker, because in the initially the head is pointing to the leftmost cell of the tape. This is followed by a string in sigma over sigma or in sigma star. This is followed by the right end marker. Okay. So what will happen? S followed by the left end marker, followed by a string over sigma, followed by the right end marker. This is the initial configuration. So what it has generated is essentially a string over sigma. But these bad things are there. S left end marker is there at the beginning, and the right end marker is there on the at the end. Let them vanish. If they vanish, what we will be left with is only a string over sigma. And since this machine, this grammar faithfully rewinded or rewound the transitions of the machine, if that machine starts with that input string in the start state S, okay, then it will eventually end up in left end marker, T prime, right end marker. That configuration. Okay. So I am adding these rules. This can vanish, and then this part I just leave to you. Okay. Change of configuration. Two types of transitions are allowed. A right transition and a left transition. Agree? You may also add the stationary transition, but it's not needed for the moment. And whenever such a transition takes place, the change is only very local. Right? A little bit of change is happening in some places at the position of the head. Okay. Now these rules, BQ can be PA or QCB can be CPA, is just simulated change, but in the reverse order. From after the transition to before the transition. Okay? To verify that these rules are correctly simulating the movement in the reverse order from end to beginning, after the transition to before the transition. Okay, so you just work it out. This is fairly straightforward, unless there is a typo. I hope this is fine. Okay, so that's it. So AIM accepts like this. S, start state is S, and the head is moving at, is positioned at the leftmost cell, that is the left end marker, followed by the input string W, followed by that right end marker. Okay. And in one or more steps, it will eventually go to this final configuration. Okay. And the grammar will do just the opposite thing. It will start from the final configuration, and it will eventually produce the initial configuration, and then S left hand marker will vanish, and then the right hand marker will vanish, eventually giving only the string W over sigma. Happy? So that's the proof basically. Only thing, I am just leaving these two verifications to you. Fairly straightforward. Okay. Okay. So yeah, maybe we will solve some 1 or 2 exercises on this from this on Thursday. Okay, so maybe again I am a bit slow. Anyway, so that's what I wanted to cover about unrestricted grammars. What now we will do, we will start this next topic. Of course, I will cover it tomorrow in detail, but let me for the moment just give you a let me give you a motivation for this. Okay. So this is going to be a very or the beginning of a very important topic. So far we have seen many ways how we can represent Turing machines. Okay. With one tape, two tape, three tape, four tape, and even two-dimensional tape. And sometimes we have seen that restricted models of computation like counter automata, Q automata, they are also equivalent in power. But then by simple countability argument, it follows that there will definitely be machines, okay, or rather languages that cannot be recognized by Turing machine. It's bound to happen. Okay. Now identifying those machines and also our ability to prove that for certain languages, no total Turing machine can exist. Okay. These two capabilities are quite, I would say, fundamental in the understanding of computation, the limits of computation. And we will deal with this topic in the rest of this course. Okay. So we start with one particular machine called the universal Turing machine, okay, which essentially looks like a machine of this kind. Okay. So the goal is something, design a single machine for solving all possible problems. Okay, like your laptop or this desktop computer. Okay. So far we have not done these things, right? For a single problem, we have generated a single machine. What you have also done is sometimes one machine is simulating another machine. So that way, the original machine, its transitions are somehow embedded in the head of the simulating machine. These two things we have done. Okay. But something like one size fits all, this kind of thing we have not yet done, right? Okay. So far we have built several machines, each solving one particular problem. Okay. And we have also embedded the finite control of a machine in the finite control of a simulating machine. Okay. But our computers are not like that. Okay. So you can think of this way. If you have an exe file, an executable file, like a.out, this can be assumed to solve one particular problem. And you simply feed the machine this executable code. Okay. It will run it and solve this problem. Now, whatever a.out is, it will solve that problem. Okay. So the computer can run any executable file, provided that it can make sense out of this executable file. Okay. Make sense means it should be a valid sequence of instructions that this particular CPU can understand. Okay. If you compile one code in, let's say, Windows and want to run it on Linux, although this is a valid executable code, this will perhaps not run. Okay. Without something like emulators and all that stuff. Okay. So this is another important thing. The executable file must be presented in a format, so-called, what is that called? Assembly language format that particular CPU understands. Okay. So I want to design Turing machines like this. Okay. So we have to understand how we can generate such executable files. Okay. And how the so-called universal Turing machine will make sense out of this executable file. Okay. Okay, so this is the question. Can we present the working of a Turing machine M as an executable file? Okay. And supply that executable file to the tape, not in the finite control of the simulating machine. Okay, so your A.out does not stay inside the CPU. It is in your memory, in the memory of the computer. Likewise, here I will convert a Turing machine M to an executable file, and that executable file will not go to the head, the CPU. It will stay in the memory. And for the Turing machine, the memory is the tape. Right? So this is our goal. And this universal Turing machine will read that executable file from the tape. I should also supply an input for that Turing machine M. Okay. So it will read both from the tape, and in some way it will simulate the working of M on that input X or W, whatever you call it. Okay. Okay. So the point is that there must be an encoding process. So M is now described by something, that executable file, and that will go to the tape. So it should be a string. And the process of converting that 7-tuple description to a string, okay, 7 or 8, whatever, that process is called encoding. So the original Turing machine in the encoded form will go to the tape of the universal Turing machine. Okay. And also we should supply whatever M is supposed to take as input. Okay. So X should also be encoded, okay, in a form. Okay. But X is already a string, its encoding is actually easier. Okay. And you simulate M on X by looking at the description of M and X. Okay. And description says whether M accepts, whether M rejects, or whether M loops on X. Whatever it does, you will keep on doing this thing because it's just a simulation. Okay. So, so this is our goal. Okay, so it's already 1. Okay, so this is another point. You does not need to store the finite control of M in its finite control. Okay. Okay, so then we should talk about the generation of this executable file. Okay. What I will do, I will encode M in binary. Now, the exact encoding is not very important, but I am just giving you one example. Maybe just give me 5 minutes. It's already 1, but anyway. So I will encode that machine M in binary, and I will supply that 0, 1 string, okay, that binary string as the executable file. Okay. So this is the formal definition of M. 1, 2, 3, 4, 5, 6, 7, 8, and 9 tuple. Okay. So let's say there are n states, and there are m tape symbols, out of which k are input symbols. Okay. So given this, I can always represent Q as the set 0 through n minus 1. That set is also of size n. I can represent sigma by the set 0 to k minus 1 and gamma of 0 to m minus 1, so that the sigma is a part of this gamma. Right. The first k symbols of gamma are actually input symbols. The remaining things are part of the tape alphabet, but other than input symbols. In particular, these two are two special symbols in the range k to m minus 1. Okay. Let me we call it E and B. These are integers, so we can call this E and B. Okay. S, T, R are three states. So they are integers in the range 0 to n minus 1 because they are parts of Q. Okay. So all these components together, except for this delta, can be encoded in the form 0 power n, giving the number of states with the understanding the states are 0 to n minus 1. Okay. 1 is acting as a separator. 0 power k. K is the number of input symbols, followed by m, followed by 1 is a separator, and all these integers can be supplied in this form. So some Turing machine, the so-called universal Turing machine, can read this description and understand how many states are there, how many symbols are there, what is the start state, what is the accept state, and so on. Okay. And then I have to supply the transitions one after another. Okay. So I can encode this thing like this. Under this thing, what is P? It is a state, so it's an integer between 0 to n minus 1, both inclusive. A is a tape symbol, so it's a member of this. It's basically an integer, non-negative integer. This is once again a member of this. B is a member of this. And L is a direction, so I may make some kind of, I would say, convention. 0 means left, 1 means right. Okay. So I encode this in this fashion. Okay. And using this in this fashion. Okay. And now I have encoded the machine. I should also encode this input string. So which AI is an integer of the, yeah, right? In the range 0 to k minus 1, because it is a member of this. So I can encode it as 0 power a1 followed by this 1, 0 power a2 followed by 1, and so on, 0 power al followed by 1. So I have an encoding, a binary encoding for this, the machine, and the input for this machine. Okay. I have to somehow separate these two. So I will append, I will insert a hash between m and x, the encoding of m and encoding of m, and feed that thing to my simulating Turing machine. Okay. Okay. So let's stop here. This scheme is fairly straightforward, and it is obvious that a Turing machine that looks into this encoding can figure out how m should behave. It does not need to have that information in its head. It can simply read it from its own tape. Okay. Okay, so I will continue with this tomorrow. Okay. Fine. So let us stop.
Thank you, sir.
Okay. Bye. See you tomorrow.